much. Thank you very much, organizers, for inviting me and this opportunity to speak. I'm an affiliated faculty with the IACS, so it's a bigger pleasure to talk to you, to introduce my work, to tell you what I'm doing. We didn't have opportunity to meet earlier, also because of pandemic. I joined the Sony group just before pandemic started, so it was an interesting time. When I was interviewed, people were starting to buy face masks, and once the interview process finished, the shutdown started. So very quickly, 2 years we were from home. Right, so probably that's also related to why I started working on face muscle analysis from videos and images, right? Remote analysis. We are all used to Zoom and having meetings via Zoom, and maybe we would wish to, to see if the people that we are meeting or teaching are happy or sad when we talk to them on Zoom, right? So that's one potential application here. Okay, so let me jump into talk. It moves good. So I will talk. This is the plan. It's a lot. I'm sure you all are familiar with neural networks, so I'm not going to spend much time on it. Basics, just for some students maybe, and then convolutional neural networks, 3D version of them, geometric deep learning. I will talk a bit about face image analysis and applications of face image analysis in general, some examples. Then the second half is the research that we did or we are doing. First, face muscle analysis using images. Then face muscle analysis using videos, my recent work, and some applications, potential applications for this new technology. And yeah, the purpose is to, I know that IACS has a lot of very interesting projects and people working here on computational capabilities. So I'm looking forward to potential collaborations. And of course, feel free to interrupt or ask questions at any time during the talk. We can contribute this side, and let's start. Okay, so neural networks. I'm sure you all know this is a simple architecture: input layer, hidden layer, and the output. You plug in the data. In each of these hidden neurons, you have some linear transformation, weights times the input plus biases, then some nonlinear activation function. You can have different activation functions. These are some examples. And that creates this linear, nonlinear convolution. And then you stack them together multiple times, and you get a feed-forward neural network where the previous output is input to the next one, and you build a neural network. Then people realized that those neural networks work much better if you stack a lot of those layers on top of each other, and you get better bias variance trade-off, better feed of those neural networks, so out of sample performance if you have deeper architectures. People initially use those neural networks for image classification, in particular handwritten digits. We will have the famous example of handwritten digits for probably for post office or for zip codes. You can imagine the application of this. And you flatten the image, the black and white image of the digit into a vector, and you push it through a neural network, and the neural network should, after the training, should be able to predict which digit it is. Unfortunately, digits, as many things can be shifted. So when you write 3, you're going to write it in different ways each time you write it. So there is a problem when you flatten it out. Your 3, any digit can be, the same digit can be encoded in a completely different way. And that's complicates the problem. Still with this simple problem, traditional feed-forward neural networks do surprisingly well. But there are bigger problems, like, for example, classification of like fashionist, where you classify different clothes, and then you need some shifting variance in these more complex problems. Okay, and that starts that that was one of the motivations to introduce convolutional neural networks originally, and 3D convolutional neural networks, and in general, to take the advantage of the underlying structure, people start working with geometric deep learning. So they started again many years ago, 50 years ago, with some papers by Pawel, who analyzed brain signals from a cat that is stimulated with some image. The first paper on convolutional structures by Fukushima in 1980, and then Lacan picked up the idea and built the first proper convolution, showed how to use these convolutional neural networks and filters for image classifications in the 1989. So modern CNNs look more like this. You have an image, you stack a lot of convolutional filters, convolutional filters, you generate some output based on the filter. You plug it into another layer, or you do some max pooling, and through a deep architecture, eventually you flatten this out and you classify. Okay. For example, for face expressions, you can classify some face expressions, or you can even use pre-trained models like ResNet, which is pre-trained on large number of images, not necessarily faces, but it still can. It's used basically as a feature extraction. You don't have to train it; it's pre-trained, and then on top you just put some classifier, for example, support vector machine, or again a simple feed-forward network with some softmax, and you can classify images based on that. More recently, people start working also with sequences of images, like, in other words, videos. Here you have brain CT scan images, and you have basically many slices of the brain image, and then instead of convolutions, which are 2D filters, you apply those 3D kernels to locally capture some information in the image, and across images filter it out. And the idea is still the same: you stack them together in many layers, and you generate some classification. You can help yourself with some additional inputs about the subjects in class. But in general, the subjects in the videos are not so static. Here, I guess the patient is in a machine and they scan his brain. The brain doesn't move much in place, but the general videos have this problem that the subject can be moving in the video, the object of interest. And that brought us to the next generalization of this concept, first from graph neural networks up to manifolds, or basically Gauss CNNs, which are some discretization. If you discretize them, they are just graph neural networks with a specific structure for the discretization. And these are neural networks with manifolds. Okay, so that's in 5 minutes the evolution of this topic. And we're gonna focus on face images and videos. So first, I will show you some applications of face image analysis. Here you have first one, commercial one. Amazon has a software. There is an API, so you can connect programmatically and send your images and get results in Python, or you can just upload images to using this GUI, and it classifies images. It's already pre-trained for you. It classifies images based on information and provide something like smile, no smile, glasses, no glasses. And it also tells you if the person in the image is celebrity or not, some things like that.
Does it do the cropping for you also? Or it do that?
It does, you just upload an image like this and you get information about all the faces in the image. Programmatically, you can specify how many people you want from the image to recognize, one more, and it will find the biggest one and do some analysis. Okay, you probably encountered facial recognition systems already in life, either at the airport where you are coming to the US or maybe some other country, the European Union or Asia. You don't necessarily are welcomed by a TSA agent, but by a machine. You put your passport and it lets you in. Or in some more secure buildings, and they might also check your identity based on face. Surveillance or security on the streets, also in New York, for example, it's a big topic that people are recorded all over the place, and some privacy issues related, but still it increases the safeness and security a lot. Other applications, so we can detect emotions from images, crowds, like conferences or meetings or for marketing purposes. You display an advertisement of a new bag or new shoes or new car. And if a person is watching and smiling and reacting to the advertisement, you just send him an email with a discount. If you can recognize the person from the image. Or you aggregate some information about the event or about the product based on what they see. Another application is lie detection. So, and this is scientifically shown that if you ask a person an uncomfortable question, even if they don't want to tell you the truth, in the beginning they will have a small tick or some expression which will help to detect the attitude of the person, the relation to the question. Another application are deep fakes. So here you have videos on the left. It's from our data set. On the left, you have a real video, and on the right, you have the corresponding deep fake. And you can see the difference in the face. Of course, this is not a very deep fake. It's a pretty shallow fake. There are much deeper fakes nowadays. I don't know, if you Google Tom Cruise deep fake, you're going to find really accurate videos of Tom Cruise. He really looks realistic, but it's a fake. There are more risky problems when people start producing deep fakes for politicians or celebrities as well. And they can influence society to posting a lot of it, right? Now there is a lot of discussion with ChatGPT as well, and the usage of this AI in a malicious way. So already some time ago, DoD launched a tool for detecting deepfakes. I don't know how well it does. It's a challenging problem. So what we do is we focus on biological information from the images or videos. So on face muscle analysis. I have a simple setup of one of the recent papers that we did and published on analysis of face muscles using photos in a very steady setup. When a person, the photo is taken on the faces in the tripod, and we display some happy and sad images to that person, and we try to identify the emotions. We're going to talk about this in a minute. So what's the approach is we conjecture that muscles of the face are directly connected to your skin, right? That makes sense. And no matter your gender, your race, your language, your age, your BMI index, your faces and skin on the face is directly connected to the muscles. So when we measure the movement on the face, we can trace back it to the underlying muscles. And it's safe in a sense. It's not going to be biased towards a certain group of people. We all have faces with the same muscles, no matter of identity and gender. So there was some work done by my colleagues already earlier, using some of those techniques that I will tell you about. They analyze patients with acoustic neuroma, which is a type of non-invasive brain tumor, which is somewhere here between the ear and the skull, and it suppresses your muscles or your nerves here and causes partial paralysis in the face, and even on an early stage. And people come to the hospital, and it's very difficult to diagnose this because the first symptoms is a headache, maybe some whispering in the ear, some noise in one ear or something like this. And most of the time it's just because the person is in a concert or in a loud room or something, or he just has a migraine, and they have to send that patient immediately to do some what's it called, CT scan, right? Brain scan, and that's very costly. And 90% cases, or 99% cases, it's not acoustic neuroma, and the insurance companies are not happy about that because it's expensive to do this analysis, and the patient has to come. It takes time, and the doctor has to see. So since this asymmetry comes out relatively early, and one of the doctors at Stony Brook actually specializes in surgeries for this type of tumor. He said that he can always, almost with his naked eyes, see that the person has or doesn't have acoustic neuroma or parallelism. So he did hundreds of those surgeries, and he really knows what he's talking about. So they picked this up and built and use these tools to detect the asymmetry in the face. I will show you in a moment what. And indeed, in a non-invasive way, it is possible. And then another application was for plastic surgeon for Botox injections, to quantify how much Botox and where to inject the Botox based on the muscle movement in the face, and also post-treatment to quantify how effective and whether the effects of Botox injections. It's also important because Botox is it's a botulinum toxin type A, so it's a toxin. So you don't really want to inject this in your face. In large amounts, it could kill you. It's very toxic. So we want the minimum amount to get the maximum effect. Basically, that's the idea. And this tools that I show you were helpful in quantifying this. And last but not least, recently we wrote a paper where we use this image analysis tools for detecting emotions. That's where I joined that group and we started looking. So what's the idea? The idea is based on so-called digital image speckle correlation, which comes from material science. You have a material, you apply some stretching to this material, and you are looking where the material is stretching the most based on the images, right? And you should get something like that. So basically, you should see which parts of the material are stretched based on two images. And so you have two images and you compare, you're looking at every pixel or some range of pixels, and you're looking for another range of pixels in in the second image, which is most correlated, most similar to the first. Okay. It's also known as optical flow in image processing. And the idea was to apply it to human face because of the skin, which has this kind of pores and freckles. So it should be possible to detect those stretches and movements in the face. So assessing facial mass, muscle, and nerve deficits in patients with acoustic neuroma, providing information equivalent to electromyography. And this EMG, it's a more traditional tool, right? You attach needles, you put needles in the face, and you measure the activation of the muscles based on signals that those electrodes detect. Right? And here you have an alternative, which is a non-invasive, non-contact, simple and cost-effective, based on the recognition of the pattern in the skin. So here we have an example of a patient. First picture, second picture, so no smile, smile. And that's when we compute this measurement. We can see how where are the biggest movements, micro movements.
So you're actually resolving the image is resolving down to the individual pore level of the skin. That gives you the registration.
Yeah. So you compute small at every small piece of the couple of pixels. You look for a couple of pixels in that neighborhood which are most correlated with the given group. And you can find this. So so it worked also for Botox injections. And here you have a patient with which does some exercises here, just neutral, now squeezes the forehead and then or rises the eyes, then squeezes the forehead. And similarly here, globular and globular because is out lifting the forehead here, you squeeze it. And the photos are taken at time 0, 1 week, 2 weeks, and 4 weeks, and monthly to 6 months. Here are just some 3 photos from that set. They did a clinical study. And here is the vector map of the movement. When the patient squeezes the forehead, and the vector map of the movement when she rises the eyebrow. This is, I think, before the Botox injection. This is some heat map of those movements. Here is pre-injection, 1 week post-injection, and 2 weeks post-injections. You can see how, when she's trying to do the same exercise, how much the forehead, the mobility of the forehead changes. Here is more day 1, day up to week 3, week 12. I don't see well here, but I guess week 16 or something like this, yeah. And you can see how the movement dies out, and then the patient gains back forever. So regain the. And there is also some things like if she couldn't move the forehead, she starts moving recruits other muscles to move. The forehead is paralyzed. And that also helped the doctors to locate the injections in better spots. So the black dots are injections based on plastic surgeon consensus recommendation. These are the injections based on the biggest movement in the forehead based on measurement. So there is some discrepancy. And they did some analysis on different patients, how based on doctors' opinions and based on their measurements, how much movement is recovered. Compared to the questionnaires and the analysis. And then the important part is the dosage, how much dose, how much within Botox, how much. Okay, so on. And then the other application was for this brain tumor, for acoustic neuroma, measuring. Again, you ask the patient to smile, not to smile, and to measure the asymmetry in the face. So here's a control, the person is very symmetric. And before the treatment, before the surgery, person with acoustic neuroma, and post-surgery. And there are different types of surgery. And some bring back maybe more symmetry, some less. So that's another application. Facial identification, I will skip that. So in general, the ability to accurately predict the internal state of the human mind remains one of the, so the next topic is subjective detection of human mind or emotions. And the way psychiatrists do it now, it's more on self-report, on questionnaires, on observed assessment, maybe some parameters like heart rate, body temperature, respiratory. So another way to analyze the emotions is we look at the face, the facial expressions, and there's all literatures which say that the face is representative for the emotions strongly. And we did that, like I said earlier, in this controlled environment. We displayed the images happy and sad. Here you have some examples to the patients, the subjects. There were 10 subjects, 10 happy and 10 sad images were displayed to each of them. And we see include photos during this experiment of the subject. And here you have an example, and try to guess where this person is displayed. A blank screen, so a white screen, no happy, no sad. When is displayed happy, when is he displayed sad? Can you differentiate? Guys, maybe once I had a person who actually guessed it correctly. Middle one is happy, okay.
And on the right.
Sad on the right, so this will be neutral. Okay, so neutral, happy, sad. Neutral, happy, sad. Very good. Another one. You can replace the image processing tools, but you can see that it's pretty hard to see. And but if we take two consecutive images and we analyze this micro movement, and by the way, we ask the subjects not to smile, okay, not to express their emotions. It's not that we are like to smile or be unhappy. They remain something like that, and then we take a bunch of pictures. They tend to micro move on the bottom of the head and move more on the forehead. Yeah, we did it for 10 subjects, and then it was very consistent. So when they saw happy images, they always move the bottom of the head. When they see sad images, they tend to move more on the top of the head. With it, taking this as an input into any classifier works very well. And we compare it with this Amazon AWS, yes?
So are the eyes blacked out just
Eyes,
because?
yeah, because these are patients and we.
Okay, but you are analyzing like their eyes?
No, we don't.
Oh, you don't know?
No, we don't. We just do the skin.
You don't have any evidence that if you hide the eye, that people cannot recognize them. I think
That's how it's in the paper. I don't know. I don't know what the IRP and all those medical documents that I was responsible. I had the matrix of the data, and I don't know what's the reason for it. I did this. So we compared against the Amazon recognition method, the software in the beginning. They have 7 states, and you cannot change that. So we had to 7 or 8 states. So we have to keep that, and the true are just free states, but still Amazon recognition couldn't find anything because it's static method. It works from one image at a time, and it doesn't detect the micro movement. And any of the machine learning methods, or however we use classifier, like sparsely logistic regression or feed-forward neural networks or some convolutional neural networks, they had almost perfect accuracy on this data out of sample. So because we saw the images. And this was very consistent across the data, across the frames, sets that had high similarity between images, happy and very high, and happy said happy, they have large similarity between images for all the subjects. Moreover, we can even quantify how they react to the image. So here you have the vertical lines are the time when the slide changes from one happy to the next happy, from one set to the next happy. You can see how when they react what they see on the screen, and how much their face moves. Right, so we can measure the reaction time of the subject to the displayed image. We did some experiments with where is Waldo, showed some students this and asked them to find Waldo, and we monitored and we waited until they find the Waldo. They reacted to that pretty well. So we can see the reaction time. And yeah, the results for happy set also were pretty consistent across subjects. Gonna skip that. So the next part, or the latest part, is how to bring it to away from this laboratory setup to a more flexible way where you can take your own video with the phone or with the camera and just send it and can be analyzed. And instead of images, right, we want to analyze videos, right? But the hypothesis is still the same. So the muscles underlying the skin are, when you measure the movement on the skin, you should have some information about the muscles. Here you have a video of a lady, we call her a makeup lady. Half of their face is covered with makeup, representing the muscle movement, the muscles, the anatomy of the muscles. Another half is visible, and you can see she's doing different exercises with her face and activating different muscles. So we're going to come back to her because we know. So what's the idea is, okay, there are those static images, one image at a time, right? There are I showed you the method which compares two consecutive images, right? So it's like almost like a video, just two images. There are also methods like if you have a phone or something where they analyze the geometry of your face, then they detect the face manifold, but they still do it once. So we have to somehow combine this with this and do analysis on the videos. Okay. So first we need some tools to do that from differential geometry, because we want to measure, even if the subject is moving, we want to measure the movement on the skin and not the movement of his head when he takes the video. So instead of flat images, we need to first find the face manifold and measure the movement on the face manifold using some differential geometry. And then what's very helpful, of course, is some smoothing, because we have sequences of images. So we can do spectral analysis in manifolds to actually, it's a tricky problem, right? Because the face is moving and we have to detect it from the videos. Maybe it's not moving so much like here, but still. And there is a noise to signal problem. I come from quantitative finance. Like in the beginning, I like to work with problems with high noise, low signal. So it was a good, an interesting problem. So yeah, we combine all this stuff. to see how much we can still do on the face. Okay, so here you can see some examples on the right. Like I said, we use the face manifold and then we measure the movements on the face based on the local coordinate system, face GPS, to detect the muscle. So here you have our makeup lady, and you can see this is a vector map. Maybe you don't, the resolution is not perfect on the screen, but these are arrows and the color indicates the length of the arrow. So the biggest movements in her face. She's doing those exercises and you can see that which muscles or which parts of the face are activated. And here, where the muscles are connected. Yes?
Are you still measuring movement based on location of the pores, or is this
Based on location of the, it's
the
just,
video to be high?
we have to do it from the, we account for the geometry of the face. We measure the movement on the surface and not on the image, right?
So if I use my phone like to do,
Yeah.
how can it, like my phone doesn't have as good resolution to like see my pores, right? Or
Oh, it does. I mean,
okay,
like any iPhone has,
okay.
I guess, a
Okay. Oh, the color map is generated using neural networks.
no. So no yet neural networks. We just do measurements. Neural networks are coming, but we do the measurements of movement, right? So basically, you can take a video with your phone. We get something like that, which traces your face, and then we can measure the local muscle.
So this is generated training data.
There is
this generated training data?
there is nothing trained here. It's
Yeah,
measured.
is this generated the training data with neural network data?
Yes, yes. So the idea is, yeah, exactly. So with this, here you have the patient, one of those hacky set. Now analyze on the video, not on images. Here is displayed the happy images. This is just the second view of what he sees. And you can see movement more in the bottom part of the face than here more in the forehead.
And the sand comes from the Stony Brook logo at the top.
Yeah, I should flip the, should be the vacuum. Maybe he concentrates on the logo. And we use that recently on a bigger data set, not only happy set, but also other emotions. And there is again, some scientific evidence saying that if you express emotions, you're going to express different emotions on your face by different face expressions. And there are machine learning models which actually detect emotions from videos without any underlying muscle analysis. And what we did is we took one of those fancy models. It's called FUN, which has, I think it's, I don't remember that one, what it stands for, but it has attention mechanism across frames, across multiple frames, attention mechanism, something like this. And the only difference that we did is instead of plugging in the original videos, we first run the videos through this algorithm. We got videos with arrows because all those models for image analysis, they have convolutional layers. Convolutional layers love edges and lines. Arrows are just edges. So it started picking that up. And we got, well, on the original data, which they used in the paper, their model works if we don't pre-train, if we use just pre-trained ResNet to generate features like they did, the FUN model works really well and they have like 96, 98 accuracy. If we train everything together, then we outperform with this, we outperform the model, the original model. And more interestingly, we injected these videos to the data set, which have less expressive emotions. They are not, they are not like that. They are more hidden. And then even with the pre-trained model, the fun plus disk analysis, so the arrows on the face, they were helping to detect emotions. So in case of more hidden emotions, that could happen. And that's the improving the accuracy. So that was the recent performance. And now I can talk a little bit about medical applications, right? The Botox injections. So obviously, if you want to do it in practice, it would be good to do it from the video, so the patient doesn't have to put his head on the tripod and doesn't have to be so clinical. It's easier to work. Post-medical, post-surgery recovery. So suppose person had some face surgery and you want to monitor how his face is recovering post-surgery. That's potential other application which we can investigate. Again, the acoustic neuroma now, because this disease is very rare, so it would be good to scan potential or pre-test potential patients from home. They can just upload their video, and if there is any kind of face asymmetry, maybe after some training to call them into the hospital. Medical, now we are working with some videos of people with strokes, Bell's palsy and ALS, and to analyze their face asymmetries post-stroke. There is a big difference between Bell's palsy and stroke. Bell's palsy is causing an asymmetry in the whole face. Stroke tends to, it's just asymmetry in the bottom half, one quarter of the face. And especially with stroke, for example, it's very important to detect it quickly and react quickly, right? So imagine you have something like that on the phone, and you just take a video. The phone knows your location, your data, your information. You can call the ambulance immediately to help you. So that's another application. You have some patients with stroke, ALS, maybe with actually stroke, ALS. And this is a lady from Stony Brook, a professor. She has Bell's palsy. Video of her. You can see some asymmetries in the face. Okay, so that's other application. And yeah, I'm starting working with some psychiatrists here at Stony Brook to analyze impact of ketamine treatment on people with severe psychological depressions. So we record them before the treatment, and then they are given a dosage of ketamine, and we look how their face muscles relax and how they relax immediately or shortly after the ketamine. We want to study how they relax in the long run. There's a long-term effect on their muscle stress in the face based on some studies. Yeah. So in general, it's interesting. There's lots of interesting applications, and this video muscle movement analysis from the videos is non-invasive, scalable, and remote alternative to facial electromyography. Well, instead of putting needles in people's faces, you can just record the face, and the video send that to the doctor, or maybe if you want to do it more carefully for movements, you have to do it maybe in the doctor's office and detect some analyzing. Okay, so I think that's it. Thank you very much.
For a quick comment. Any more questions?
I have a question. Why when the person move his mouth right, then the right is right, but when he move his mouth left, then the middle is right.
So you're saying that if he moves here, then this doesn't light up so much.
Yeah.
I guess because this moves more, right? Because these are relative measures. So it gets red because that's a bigger movement than on the others.
I mean, when they move left or right, the lighter part is not symmetric.
I mean, if you
That's a suspicion.
so you mean why? Because his face is asymmetric. He's a little bit asymmetric.
Everybody is not perfect.
It's not no, yeah. That's another way of detecting deep face, maybe. If it's too symmetric, it's suspicious.
That's right.
You didn't do it live in the beginning. Is that didn't go less they explored or is
No. We
no medical
I think
imaging.
we didn't have yet any
Yeah.
experiments, liars, stuff. But there, I mean, what is robustly explored is that there are papers which are saying that people, when they are lying or telling some, dishonest things or answer questions, they have this micro movements in their face first. Right, so there's all those raised eyebrows often sign discomfort if their voices goes up or down, so there's eye contact shows. But if they look into your eyes, crossed legs, shaking legs, okay, so there are different things, but this part of movement, right? So face detection, and then slight movements in the face expressions immediately after the question, they indicate something.
Sure, but you're saying the science has been done on that. Yes. Thank you.
And that's from the FBI handbook.
Yeah, I showed it to, there was a military coming to Stony Brook. I showed this. They were interested, but then they asked me if I had a citizenship. I said, I'm still in the process. I said, okay.
Okay.
Yeah.
Yeah, thanks a lot for the presentation. It was really interesting because I didn't know anything about that before. It's really interesting. Can imagine that there are a lot of use cases. And I actually have a question. When you link this micro movement to an emotion of a person, is this valid for everybody in the whole world, or does it depend on ethnicity, race, or the society they were raised in?
I mean, so this, what we did here, it had, we didn't do it on different countries, but the subjects, they were definitely different races. And so we had people here from Asia. You don't see it well, but yeah, there were some Arabic origin people. One person was from, I think, Iran. One person was from Asia. We have, yeah. I
That's
think,
interesting because I think people have different.
but subtle,
Yeah.
they emotional states also depend. So it's not even race. It's it could be that if you are more emotional, or like we are now looking at this ketamine, they're going to react much more post ketamine than before. Yeah, but what is common is this here. This type of classification is pretty old. When people are experiencing certain emotions, they react, their faces react differently. And even if it's maybe less strong reactions, they should still have some movement in that region. And at least for happy set, it was really easy, up, down, so that was possible. Yeah, noise to signal. So for stronger reactions, like I said, there are methods which work pretty well, and you don't maybe need to analyze those muscles. But if you want to capture more subtle emotions, it doesn't hurt. The other reason is those arrows, they cover 10% of pixels or something like this. So they don't really affect the performance of the original models that much because they don't take so much space on the image.
I think my question is similar. Do you know the accuracy of detecting those subtle emotions when there's a criminal sitting in front of you and you ask questions, you detect the subtle emotion to detect whether he was lying or not?
I don't know. You didn't get interview. Criminals. No, we run this on the standard data set and injected our data with hidden emotions, and that's the accuracy that we got. On cross validation. So these are average cross validation for this sort of stuff.
And the visual muscle, which part is reactive, is case dependent.
No, the idea is that you more or less gonna react similarly across subjects to the same emotion. I don't remember the amount of subject here, but it's pretty large. It's a standard data for emotions analysis. CK++, and then just added.
We augment the training data.
Yeah, we added the training data, training and testing both. Right? And because in each of those we added, I think, because there are 20 emotions videos or 10 subjects, 10 slides per emotion, 20 videos per subject, 200 videos. So we added 20 videos into each group, short videos for a given slide, a key set and given subject. And we trained fun on that new data set, original model. And then we trained fun after running the arrow, the muscle movement detection, and the fun performed better when there were arrows in the videos, all of the videos.
For example, if a person is actually sad, but he pretends to be happy with smile, but we can say he's not happy at all, then in this case, what will happen for the detection?
So, if you smile and you are unhappy and you force a smile, then yeah, probably you're going to classify you as happy. The same if you wear a face mask and able to see your emotions. No, yeah, so, but there is also, if you show the picture, there's in the beginning, even if you want to smile, you will probably express some, with the forehead or something, the sad emotion, seeing like. So there were some, this is actually funny, if you watch this. Yeah, so it's gonna play, no. And then go back. No, one more. Okay, so he's gonna see some happy images of kids, little babies. So the first few, he's gonna be very happy, but eventually he's gonna get tired of those babies and he starts gonna react. So he's like, yeah, he's happy, and then he's like, okay. So
More questions here? You do it. I think
You have a question? So I was trying to understand how this works on your face. So
yeah,
I'm assuming you're using pores because they're like indented, so it's darker than.
there's some texture on the image, basically. Some, it's not just one surface with the same pixels, so we cannot see what moves, what doesn't. But we have some surrounding, and there are different colors of pixels, different shades levels. So we can look where the same shades level are in the next frame or in a couple of frames maybe.
What if you, so like, he has wrinkles on his forehead, right? So that's like past the shadow. So now the color is very, all of a sudden it's like really dark. So how can you match that to what it was before it was?
Right, so your question is okay, because there are shadows. As long as the shadows don't move in the video, so the lightening is the same for the whole video, then it doesn't matter. The shadows just they stay on the video in the same place, right? They don't change the location. I mean, if you have some really bad shadowing, right, then you will have problems, right? Or if you have low light, yeah, you need light. You need light. It is motion sensitive. It's light sensitive. It's yeah. You have to do it. There is, if you want to detect those tiny movements, it's better if the person is really not moving much. If you want to detect muscle movement, for Botox injections, and some other applications like that, you can take a video from your head. Yeah.
Yeah, I think there was a question on Zoom. in chat.
Yeah. Let me answer the Zoom. Any comments on the latency and performance of this approach? Okay, so speed. Yeah, so speed is important, and I mean, it's not real time. Okay, there is a lot of computations. We did it using Python and some libraries which are in C or C++, but still there's a lot of space for improvement for sure. I work with a PhD student who is was a master in statistics, not in computer science. So obviously there's still a lot of space to speed this up. And we run those models on a desktop machine with a good graphic card. That's it. So I don't know, a video like this, probably an hour or two to get the results. But you know, for medical applications, once the train model, if you need train neural network, it's already faster to classify the result. When you get the arrows, it takes some time. But for medical applications, it's anyway faster than a CT scan where you have to go to the hospital next day to pick up the results, or whatever, a week later, meet with the doctor. So maybe to speed it up, definitely there is still a lot of space. And it also depends how many arrows you want. If you want to really analyze every little movement, then it's going to take some time. If you want to get a little bit of information in the face, you can do it faster.
Well, there is another question.
Thank you.
Okay. So, I think this.
Following from the last few people's comments, one problem of attempting to study emotion through facial expressions is that facial expressions are social and cultural, like whether people smile and how their smile looks, for example, has a history that is different for different countries and genders and social identities. This surely creates ethical concerns and complex. Emotional experiences might get, do you see what I'm reading? No, you don't. How do I make this visible? I can't. Maybe I can.
You're right. So the other one.
So yeah, I don't know exactly that. Those ethical problems, but ethical when complex emotional experiences might get reduced to simple labels that seem to offer kind of extra vision of how people really feel. How you choose the images that are assumed to trigger a universal response of Becky and said. Okay, so those images, first of all, those images, they were obtained from some standard library of images which are classified by psychologists or psychiatrists, experts to trigger those emotions or to be happy or positive and negative images. I don't remember now the name, it's in the paper, but this is like a standard tool to use. And my co-authors who are medical experts, they did that, they selected them. We shared images of smiling babies and think about, okay. Right. Yeah, we picked images which, or we used the database which was standard, and yeah, it's a database which is very, very strongly affecting the subject, because they are usually, especially the sad images are pretty strong. Yeah, I mean, the results were also very robust. So if there are less emotions, they're going to react less. We're not going to detect.
All the time, let's thank the speaker again. I hope that we can stick around. I don't know whether